ICA, or independent component analysis, is a technique for separating a signal that comes from multiple sources into its individual components. This can be used for many different things, but the classic example is the cocktail party problem. Imagine you're at a cocktail party and there's a ton of different sounds going on around you. There's the person who's talking to you, there's conversations off in the distance, there's some music playing in the background, and maybe you can hear some cars driving by outside. Our brains are really good at figuring out how to focus in on just one of these sounds and tune the rest out. How might a computer do this though? If we have multiple sources of audio, is there some way that we can separate them out into their original independent sources? The answer is yes, with the use of independent component analysis. There's some fundamental assumptions that we have. The sources need to be independent, they need to be non-Gaussian or non-normal, and we need to have as many signals as there are sources, where each signal is a linear combination of each of the sources. So, for example, if we're talking about audio recordings, the audio recorded by each microphone is considered a signal, and each thing that's making noise is considered a source. First, we'll try a simple example in R where we take two sounds that are actually completely unrelated, and we'll verify that this works. Next, we're going to do a real-world example and put ICA to the test. So the first thing I'm going to do is set my working directory to the location on my computer where the files that I'm going to be working with are saved. Next, I'm going to load in several packages that we'll need for this example. So the first one is called Fast ICA, which we'll be using to perform independent component analysis. Next, we're going to be using the TuneR package, which is for loading in WAV files. Next, I'm going to be using the CWave package, which is for saving WAV files. And finally, we'll be using the audio package, which is for playing audio files from within our studio. Next, I'm going to load in the audio files that we're going to be working with. So I'm going to call the first one Signal 1. I'm going to use the read wave function from the TuneR package. And the name of the first file that I have is artificially mixed 1.wave, and signal 2 is going to be artificially mixed 2.wave. So I've actually gone ahead before starting this video and I've already artificially mixed these two files together using an audio editing software. So next we're going to play those sounds just so you can hear what they sound like before we do anything to them.
This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org.
So I'm also going to want to save the sampling rates for each of the two files, just in case they had different sampling rates, such as if I was using two separate microphones. So if we take a look at what these sampling rates are, we can see that in this case, they're actually the same. When we do the real world example later, we might see that the two different microphones will actually have different sampling rates. So that's why this is very important. Next, let's take a quick look at what the actual files look like themselves. So this is what the Signal 1 file looks like. It's got a recording for both the left and right. So it's a stereo file. That's why there are two plots that look the exact same. And then here's the plot for Signal 2. So you can see that Signal 2 comes across as much louder. So the top plot is for the left channel and the bottom plot is for the right channel. So now that we've got these sampling rates saved, I'm going to go ahead and save just the signal in this object, since we won't need the other components that are saved in this object currently. So I'm going to reassign signal 1 to be the left signal in the file. And if you have a file that's not stereo, the left and right channels are going to be exactly the same when you load them into R, so it doesn't matter which one you pick, and we're just going to pick left in this case. So the next problem is that these two signals might not be the exact same length. So even though they might be roughly the same amount of time when we record them on our computer, it's possible that they might be off by a very slight amount. So what we want to do is check which one is shorter and then make them the same length. So we're going to make both of them the same length as whichever one is shorter. So the length of the shorter file is going to be the minimum of the length of the first signal and the length of the second signal. Next, we're going to combine our two signals into a single matrix, which is actually required when we use the fast ICA function from the fast ICA package. So I'm making a matrix called signal combined, and I'm going to bind two columns together in order to create a new matrix. So the first column is going to be signal 1, and the second column is going to be signal 2, and we're just going to make them the exact same size as one another. So for signal 1, I'm going to index, and I'm going to take every observation from 1 to the length of whichever of the two files is shorter. And same thing for signal 2, I'm going to take all of the observations from 1 to the length of the shorter of the two files. So next I'm going to use the fast ICA function to perform independent component analysis to separate the two signals back into their original two sources. So the first argument I'm going to need to pass is the matrix that contains my signals, which is the single underscore column matrix that we just created. Next, we're going to need to set the number of components that we'd like to be extracted. So since we had two original sources, we're going to want to set n.comp to 2. And then we also want to set row.norm to false. So the separated object that we just created is a list, and the element S is going to be the matrix that contains the separated sources. So the first column is going to contain the first separated source, and the second column is going to contain the second separated source. So now I'm going to scale both of these by their maximums, and this step is incredibly important. If you don't do this and you listen to the sounds, you're going to hear a lot of static. Next, I'm going to play the sounds.
This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org.
And finally, we're going to save the new files. To do that, we're going to use the save wave function.
Now, we're going to create our own example, which would be more representative of a real-world situation that you might come across. We're going to use the following setup. I've got two microphones in this room, and each one is going to record some audio. I'm going to call the audio recorded by this actual microphone, signal 1, and the audio recorded by my laptop microphone, signal 2. Now, in this room, I'm going to have two different sounds playing. The first sound is going to be some royalty-free music playing out of my phone, which I'm going to place near microphone 1. The second sound is going to be coming out of another phone, and it's going to be a royalty-free audiobook. And I'm going to place the second phone near my laptop microphone. Now I'm going to go ahead and record on both of these microphones. I'm going to play back both of these recordings one at a time. Here's the signal 1 file, which was recorded using the actual microphone. And here's the signal 2 file, which was recorded using my laptop microphone. Since the music was playing really close to the actual microphone, you can hear it quite loudly in the signal 1 file. Similarly, you can hear the audiobook quite loudly in signal 2, since the second phone was very close to the laptop microphone. Even though one of the sources is much louder in each of the audio files, notice that you can hear both sounds in both files. One sound is, of course, more of a background noise in each file, but you can still hear the background noise nonetheless. If you think about it, each audio file, or signal, is a linear combination of the two original sources. The coefficients depend on how close each source is to the microphone. For example, signal 1 recorded by the actual microphone might be composed of something like 0.9 times royalty-free music plus 0.1 times royalty-free audiobook. So now let's say I had these two audio files and I want to separate out the two sounds. In other words, let's say I want to create a new audio file that contains just the royalty-free music and another new audio file that contains just the audiobook. To do this, we're going to try to use ICA.
Okay, so this time I'm going to be using the same code that I used before, but I'm going to change the name of the files. So my first signal is going to be from the actual microphone, and my second signal is going to be coming from my laptop. Now I've actually gone ahead and edited these two files a little bit in order to align them a bit better so that they start at roughly the same time. So now I'll run all of this code. So this time I've actually saved these files as mono instead of stereo. So I'll just plot those really quickly so you can see the first signal and the second signal. So they look very similar. I'm also going to save off these files. So I'm going to use the same code from before, but since this time we're not using artificially mixed sounds, we might actually have different sampling rates because we are using two different microphones. So while that's not the case for my specific example, that might be the case if you're doing this at home. So what you want to do is manually set the sampling rate for each of the files as you save. And then I'm also going to rename these files just so that I don't overwrite the ones that I created previously. And this is what the separated sounds sound like.
My darling child, she cried. She woke up and saw Dorothy running toward her. My darling child, she cried.
Clearly, the real-world example did not work as well. ICA works really well for signals that have been mixed using a computer, but less well outside of this context. It turns out that this is still somewhat of an open problem, and neural networks are part of the solution.